Swayam Prabha. Digital India. Educated India.
Welcome you to the next class on the inorganic chemistry of life, principles and perspectives. Last two classes I have tried to cover some highlights of all the topics that I have discussed, and looks like I will have one more class, maybe another class too, to cover. Initially I have covered all the highlights of the introductory aspects, then I have covered the introductory aspects of the highlights of the alkaline earth, and then vanadium, then manganese. So, let us start with iron in the bioinorganic chemistry or the biological inorganic chemistry, the highlights. The highlights in case of the iron are something arising from two categories of enzymes called heme based and those which are not having heme, and all of these are involved in oxidative reactions, reductive reactions. So, therefore, oxidoreductase reactions. They are also involved in transport reactions of oxygen, electron and iron. So, therefore, we have a huge plethora, huge list of enzymes present under the iron category, and that is where you see, if you look at the amount of the element iron present in the body is almost much higher than any other trace element, which is about 3 to 4 to 5 grams per a body weight of 70 kilograms of body. So, that means a huge number of iron enzymes are being involved, and since it is a highlights, I just give some other things. I explained a lot of features dependent on the transport of the oxygen. I have tried to compare transport of the oxygen with respect to that of the storage of the oxygen by myoglobin, and then I compared the hemoglobin with the hemerythrin and the hemocyanin, which is in invertebrates and which is in molluscus. So, therefore, you have the hemoglobin, you have the porphyrin, and these are two non-porphyrin with the two iron ions and two copper ions. So, the kind of oxo species is iron OO, which is not so much perturbed with the oxygen-oxygen bond in case of hemoglobin, and in case of hemerythrin it is more or less like a HO2 kind of species, so hydroperoxy kind of a species. And when you go to the hemocyanin, it is basically a peroxo species. In fact, these can be very well established by variety of spectroscopy, including vibrational spectroscopy too. Okay, aspect of interest in this is that you see that the oxygen nature is differing from one to the other. So, when it comes to this, it is a weight O2 2 minus. So, when it has to act as a O2 transport, obviously it has to release not O2 2 minus, it has to release at the end O2. So, therefore, there has to be re-oxidation of this, and which is taken care in those enzymes. Whereas, in the enzyme of human, this is very slightly perturbed, and based on the conformational changes, it can get back to the simple O2 and the O2 is liberated. So, therefore, the protein conformation itself will take care of, ensures that the O2 is released, not the O2 minus or O2 minus dot kind of thing. Okay, also I have explained about the iron transport by transferrin. Transferrin has got two sites, C terminal site and terminal site, both the sites iron is bound. Important point is, in these cases the iron is bound only when carbonate ion is present, and we know that it is an allosteric factor, because in order to form the metal core you require the carbonate factor that we have seen. And these two N terminal and C terminal differ by very small change in their strength, and this is indeed reflected when these are released too. Okay, so the receptor sites of the cell membrane will receive the transferrin, which is bound with the iron ions, and will basically make a vesicle and engulf inside. So, once it is engulfed inside, as the pH changes, the iron ions are released. Initially the N terminal ion is released at a slightly higher pH such as 4.5, and at 3.8 the lower, at a lower pH which is around 3.8 C terminal is released, and this is how the iron transport in fact takes place. Followed by this, I have talked to you about the iron storage by ferritin. Ferritin is a huge protein having 24 subunits, 4,500 iron ions, about 7 to 8 nanometers diameter, and there are two major features. One is threefold access of channels and fourfold access of channels. These are the lifelines of the ferritin. So, these will carry ions from out to in or from in to out. It could be ions, it could be reducing equivalents, etc. All of these things are being. In fact, the way, if you see the lining inside, as the iron 2 plus enters in, iron 2 plus binds to the carboxylic terminals interior, then oxidized by the oxygen, and then further bridges by the phosphate. So, you get basically some kind of a iron oxophosphate kind of a bridged kind of a species which will grow from one to the other. And when you release this by using the reducing equivalents, again iron 3 plus is reduced to iron 2 plus, and then the iron 2 plus come out. I am sure you know why it has to be converted to iron 2 plus, because iron 2 plus is highly mobile as compared to, or labile, rather use the word labile, as compared to the iron 3 plus. So, that is where the things are happening, and entire thing is very orderly fashion. It happens, both the formation of the iron cluster formation inside as well as the release of this forms very highly. So, therefore, you have entry and exit the iron from the, so it enters as iron 2, stays as iron 3, but releases as iron 2 again, and this is what you need to remember. Followed by all these transport phenomena, I have come to the stage of the electron transfer to be introduced. I have introduced electron transfer. Of course, electron transfer depends upon the potential difference between the donor and acceptor in terms of delta G 0. So, as long as the delta G 0 is negative, then this is feasible kind of a reaction. What else does it depend on? It does depend upon the distance between the donor acceptor, it does depend upon the conductivity of the medium between the donor and acceptor, okay. And it also depends upon the reorganizational energy. What is the reorganizational energy? That is, you see that when the donor acceptor come close by, you get a donor acceptor complex, but that donor acceptor complex may not be in a good posture to transfer the electron. So, it has to change its posture, and this posture change is by the conformational change or reorganization. So, this particular energy difference is referred as the reorganizational energy. So, the smaller this value, the greater the rate of the reaction is there. So, these are the factors that are thing, and the cytochromes are involved, and when the cytochromes, both the 5th and 6th coordinations are blocked by histidine or histidine methionine, then these are not suited for oxygen activation, these are suited for only electron transfer. So, what kind of an electron transfer? Electron transfer from iron 3 to iron 2. So, in effect, any cytochrome C can only transfer 1 electron, not more than that. If somewhere 3 or 4 electrons are required, that means 4 times it has to work, 3 times it has to work, etc., etc. And then after having looked at the heme based electron transfer proteins, I have taken you into the iron sulfur proteins, 1 iron 4 cysteine which is called rhodioxin, 2 iron 2 sulfides which is called ferridoxin, 4 iron 4 sulfide called again ferridoxins. And these sulfides can be easily understood by adding mineral acid which will give H2S, and your nose can smell that good enough. And there are systems where protein have got 1 4Fe4S or more than 1 4Fe4S in the same, or a combination of these kind of things, etc. And these differ in their redox potentials of that. And in some of the cases, these iron sulfur proteins clusters are buried inside and stabilized by hydrogen bonds. There the redox potentials are more positive. Such things are known as the high potential iron sulfur proteins. And as you can see overall from here, whether you have a 1 iron, whether you have a 2 iron, whether you have a 3 or 4 irons, you always have only one facile electron transfer. In 1 iron, obviously there is the same reduced and oxidized. When you have 2 iron, There are three possibilities, but not all three possibilities are found in enzymes. Only these two possibilities are found. So, one iron 2, one iron 3, both iron 3, not with the both iron 2, because a highly reduced enzyme could be dangerous to the system. Similarly, when you have 4 ions, there are many combinations are there, of which the combinations that are possible are between this and this, okay, Fe reduced, Fe oxidized, and if the protein is already in the Fe oxidized, then it can be superoxidized. This is in the normal ferredoxins. And if you have a high potential iron sulfur protein ferredoxin, it can only go from 3 iron 2, 1 iron 3 to 2 iron 2 and 2 iron 3. Never it goes to this at all, never it goes to this at all. Okay. So, therefore, several of the oxidation states of these are not accessed by the system, because the system will get too reactive kind of a species, and unwanted things can happen. So, that is where the thing is. In fact, what happens in that, if you see that as you go from this cluster to this cluster to this cluster, you have 1 minus, you have 2 minus, you have 3 minus. So, your the number of reduced in this is the 3 iron 3s, 2 iron 3s and 1 iron 3, and that is how it is. As you reduce, that means you add electron, this particular bond you see that is increasing, this particular bond is also increasing, okay. And so, therefore, the core is expanding, and if you go in the reverse direction, the core is reducing. So, the core expands and the core reduces, expansion and contraction, not reduce, contraction. So, expansion and contraction in this will take the electron transfer to a kind of a useful thing. So, during the electron transfer, the core of the iron sulfur cluster expands and contracts, and that reflects in the conformational state of the whole protein that is being surrounded that. Having explained the electron transfer, then I have smoothly taken a transition into this the oxygenase enzymes. We have the monooxygenases, dioxygenases, both oxygenases based on the heme, not based on the heme. All of these are there in the iron, and I try to look at explain you at one example at least of each of these things. An example here given is cytochrome P450 and nomenclature, etc. I am not spending time here, as you know, this is from the absorption wavelength, etc. Okay, some important features in this monooxygenase. Monooxygenase means only one O atom of the O2 is added to the substrate, the other O atom of the O2 goes as water. In case of dioxygenase, both the O's of the O2 are used for the substrate oxidation, and that is what the thing is. So, the iron enzyme in the iron 3 form is this is the resting state. When the substrate enters into the close proximity of the iron center, there is a conformational change, and this triggers the electron transfer. That means enzyme is activated. So, that means after the substrate comes in, only the electron transfer takes place, because after the electron transfer takes place, the electron that is being added to the iron 3 becoming iron 2 is very active species. Therefore, that is ready to give away the electron, therefore, O2 has to be ready in that. So, then O2 1 electron, then second electron, etc., and then goes through the via ferryl oxo, and then it will add an hydroxylation to the substrate, and the water will go. So, this is interesting. Suppose one were to say that here the question is, if the substrate does not come into close to the enzyme, and if enzyme receives electron, is there any danger? There is a great danger, because if the substrate is not there, electron comes in the contact, if the oxygen is present there, then oxygen will get activated and you will get oxo radicals. Therefore, those superoxide radicals are dangerous to the system. The system can get hydroxylated. It can be the same protein can get. So, therefore, the nature has chosen the mechanism in such a way that first the entry the substrate and then followed by these things. Let us look at an example for the another example. This example, cytochrome P450 is used for camphor, many other things, but one specific one which is converts the methane to methanol is called the methane monooxygenase. And methane monooxygenase is, unlike the cytochrome P450, is not a heme kind of a protein, it is a non-heme enzyme. As you can see, in its resting state, it is in the di-iron center, and this di-iron center is obviously activated in presence of the of course substrate, which is not shown here, but I tell you it is there in the schemes that I have given you, and then takes up 2 electrons, and the 2 ions, 2 3s will go to 2 ion 2, and now it is very well poised for O2 to be oxidized, O2 to be reduced. So, the O2 can bridge between the 2 ion 3s and then receive 2 electrons, therefore, you get some kind of a peroxo kind of a species, and this will convert to the ferryl kind of a Fe4 kind of a species with oxygen bridging. So, you are going from ion 3 to ion 2, ion 2 to ion 3, again ion 4. So, 2 to 3 to 4, and then this will take your methane to methanol, and the one of the other oxygen goes as the water, and that can circulate. So, some similarities you can find between both of them, but in case of methane monooxygenase, it is not 1 iron, it is the 2 iron centers. Okay, also explain an example for the dioxygenase. An example I have taken was a protocatechate 3,4 dioxygenase, and this is again a non-heme enzyme. This is again a monoiron center enzyme, and this enzyme has got a 5 coordination with some kind of a tyrosines and histidine bound, and wherein one of the coordination can be sort of expanded for the binding of the catechol into this, and the property of the catechols is that you have a phenolic moiety, they can undergo phenol keto or enol keto kind of a tautomerism, which will go through the radical neutral kind of a species, ionic species. So, binding through mono, then becomes dentate, and now this can be activated by this particular electron, and then electron is introduced into the O2 at this stage. The O2 is introduced between the ion and this substrate, and then substrate finally gets cleaved by taking both the oxygens into it. Okay. So, in all these the redox chemistry occurs by NADH, then FAD, then 2 ion 2 sulfur, another 2 ion 2 sulfur, and the active center too. So, we have looked at various, there are other dioxygenase enzyme I have not shown in the highlights, was the tryptophan oxidase kind of a one. So, therefore, in that case it is a heme based enzyme, and that also I have given in the class. So far we have looked at the oxygenase, then I think we need to look at some of the reduction chemistry. So, ribonucleotide reductase has got a dinuclear iron center. The role of this is stabilizing a radical from the tyrosine, which is very close by within 5 angstroms from this one, and it is this which is involved in the activity. This will generate a radical at the cystenyl center, which is in a neighbor subunit, and this radical is transformed to this particular center, and from this center it is transformed to this center, and then you have a oxygenation, and then goes on this. So, the role in this particular enzyme is not a direct catalytic, it is an indirect, but it stabilizes the tyrosine radical, and rest of the things goes like the consequential steps as shown over there. Okay. So, radical formation, etc., and this radical is transferred to this particular position, and this is again racemized to that, and then oxidation, etc., and then this will lose the oxygen, and then hydrogen comes into the reduction. So, you have the dithiol and going into the disulfide, and then again back to the dithiol. So, this is one thing, and this is the radical, and radical is transformed. So, this whole thing happens in one subunit of the protein, this whole thing happens in the another subunit. This is a binding subunit plus the radical which is being transferred subunit. So, this can recognize the different nucleotides coming into the into the protein. So, therefore, you can identify the deoxyribonucleic acids that are coming into the system too. Okay, some additional highlights on the iron enzymes start taking their shape from let us say other kinds of reductases. See here example cytochrome C nitrite sulfite reductase. So, sulfite SO3 minus to HS minus, this is a 6 electron 7 proton reaction. Nitrite to ammonia, this is a 6 electron plus 7 protons, this is ammonia and 2H2O. And this kind of things, you know, you require a lot of number of electrons, therefore, simple heme are not sufficient enough. Therefore, these hemes are connected with the iron sulfur cluster, and such a situation is called cyroheme. So, cyrohemes are important, essential for doing such a huge level of the reduction. You see 6 electrons, there is a proton. So, how do you find out electron proton combination in a redox process is just by looking at the redox potentials as a function of pH. These are called Porbach's plots. From this the slope you can identify the number of electrons versus the number of proton ratio as well. It is very powerful, which I explained in the beginning. So, we have cases where the iron sulfur clusters are there, we have cases where the iron hemes are there, we have a case where both of these are present simultaneously together in the nitrite sulfite oxidase too. Another bit more the complicated one which I talked to you was in the previous slide was the nitrite reductase, and this is NO2 minus 6 electron 7 protons give NH3 and 2H2. Okay, so the resting enzyme in iron 3 with water, and in presence of the electron, first electron, it gets activated. Once it is activated with the first electron, it is ready for binding to the nitro group, and this nitro group will displace the water that is present at the iron center. Now it is ready on the platform. Now it has come into the basically a kabaddi court. So it's basically like a this is the court is getting ready. The player is entering here and then ready with the playing for the kabaddi kind of a play, and then it goes with the proton electron kind of a sequences here. NO2 binding reduction, another reduction, and then makes this one into the Gen O, okay, and then H2NOH, like somewhat like hydroxyl amine species, and then where you lose your water and then the ammonia, etc. So that is how it is. Basically you have to lose the ammonia and water. One water is going in the first step, and the second water goes at this particular thing. So that is where you have, this is the O2 water, and then you have these steps where the electrons. So you have totally the 6 electrons and 7 proton kind of a situation that you have. So therefore in the active site is +2 and resting state is +3 for the iron in all these cases. So essentially what we have looked at in the iron enzymes, huge number. We have looked at the transport of oxygen and storage of oxygen, transport of iron, storage of iron, all of these, transport of electron, transport of electron by cytochromes, transport of electron by iron sulfur proteins, how the iron sulfur clusters expand and contract during the electron transfer, the irons 4 iron 4 sulfur clusters, pyridoxine clusters. Okay, so oxygenase, then I took the cases of oxygenase, monooxygenase and dioxygenase. Monooxygenase, both the heme and the non-heme is methane to methanol. Dioxygenase is that where the protocatechate case, and I have not in the highlights explained, but I explained in the regular class the tryptophan oxidase, all those things. So absolutely, which is a heme based one too. Then I took over a lot of the iron di-iron enzymes, explained the reductases, ribonucleic reductase very well. Then I have also explained the nitrite sulfate reductases, all these where multiple electrons are required, where cyroheme is involved, and then I've also explained in the regular class rubiretrin, and I've also talked to you about the hydrolase kind of thing, which is purple acid phosphatase and this, which in the highlights I have not covered, but I have covered in that kind of a situation. Okay. So, iron is a huge story of all these kind of things. So, we have a very nice highlights of this, and please be advised in the highlights I may not be covering all the enzymes. So, I am just trying to take some features to bring to your notice. So, following this huge play with the iron for over 7, 8, 9 classes or so, then I entered into the cobalamine story, where the cobalt ion is involved. Cobalt ion is involved in the entire bioinorganic chemistry in only one aspect, that is in vitamin B12. Vitamin B12 is a coenzyme, it is not an enzyme. But this coenzyme is associated with a huge number of enzymes in bringing 1,2 hydride shift kind of a reactions. So, this is a adenosyl cobalamine is the natural one, and as you can see here, this is the corine part, and this is the benzimidazole part which is bound, and this is the group which is the one which will play a role, and therefore this bond CO to R bond can break homolytically with dot dot cobalt 2 and R dot, can break heterolytically cobalt 3 R minus, cobalt 1 R plus, and both of these are possible, all these three. These three situations are possible based on the binding strength and the protein that is there, how it is influencing the strength of these ones, and this all we have studied in the class. We have explained how the 1,2 hydride shift will lead to the product formation. In some cases there is the water elimination and other kinds of reactions happening in that too. So, adenosyl cobalamine is also involved in reductase activity, like ribonucleotide reductase activity, which is very similar, analogous to that found with the iron enzyme. So, with the iron reductase. So, therefore, I have not taken too much of importance to introduce that in this highlights at all. Okay. And so, following this, I have talked to you on nickel enzymes. I must have spent about 3-4 classes on this. We have hydrolase kind of enzymes like urease, hydrogenase reaction, dehydrogenase reactions, methyl coenzyme reductase, superoxide dismutase, glyoxylase, cis trans isomerase, and acetyl coenzyme A synthase. So many different kinds of enzymes have been covered under the nickel, and nickel is also a very important enzyme. Urease, it hydrolyzes urea to ammonia and H2CO3. Hydrogenase is the proton to hydrogen using the electrons, and it is a reversible kind of an enzyme. And CO dehydrogenase is carbon monoxide dehydrogenase going to the carbon dioxide kind of thing. Methyl coenzyme M reductase would reduce the coenzyme methyl group to methane moiety, and that methane is further used by the methanogenic methane used using bacteria, or even methanogenic one, where the methane is converted to the methanol methane monooxygenase, etc., etc. So, nickel also involved in superoxide dismutase, and you know very well superoxide dismutase. In the first step, O2 minus dot will lose the electron and go to O2. In the second step, it will take another electron and go to O2 2 minus. So, there will be effect, you will get one H2O2, one O2, and H2O2 is taken care by the catalase afterwards. So, there is a glyoxylase enzyme, cis trans isomerase, and acetyl coenzyme synthase of it. Kind of a course, you see that a dinuclear nickel with a bridge, the carboxylate hydroxy, this is used in the urease, and this is nickel in centers factor F430, which is involved in hydrogenase kind of enzymes, etc. and again these things are there, nickel iron centers, and these are in the hydrogenase. Carbon monoxide dehydrogenase, which is having different kinds of centers as you can see, and these are involved in the reactivity, and this is the superoxide dismutase. So, if you look at the nickel hydrogenase enzyme, there is a activation cycle, there is a catalysis cycle. So, activation cycle, catalysis cycle, if you follow, it is very interesting, it is very simple and easy that you can understand. I have already explained to you in SOD, nickel 3 plus, then O2 minus. So, O2 minus will bind and take out this one, go as O2, gets O2 minus get oxidized, and then Na2 plus 3 plus gets reduced to Na2 plus. This will take another mole of O2 minus, and that will reduce further. So, therefore, the nickel gets oxidized and then goes as H2O2. So, as I have mentioned all this. So, one of the important enzymes, which is a very complicated kind of an enzyme, is that the carbon monoxide dehydrogenase, where you can see it starts from this cluster and the electron flows go through this, and then finally CO and CO2, and this is shown for the reverse kind of a system. So, huge clusters of iron sulfur clusters are there in this. So, I have a few more highlights to cover, then I will start with the tutorials in the next class. I will complete the remaining highlights and then get to the tutorial. Thank you very much.